wanted to give a little introduction of our first speaker, who is Marit Solveig Seidenkrantz. She is a professor at Aarhus University since 2013, but at the university since a longer time, since the end of the 90s. Marit Solveig is an expert, so she's a micropaleontologist with an expertise in Arctic foraminifera, and a paleoclimatologist who worked on past interglacials and ice sheet dynamics and general ocean circulation, this kind of topics. And so Marit Solveig, we are very, very happy to have you because you are a strong research leader in our field. It's really impressive what you have done. And I know you are involved in the Intimate network since a long time. So it's really a pleasure to have you here today. And I'm sure you will give us an excellent overview on your present and past research. So today you will present about the deglacial and Holocene changes in ocean conditions and interaction with the cryosphere based on marine sediment records from northeast Greenland. And the floor is yours.
Thank you very much, Cecile. I will share my screen. And is it working now?
Yes, very well. Thank you.
Okay, thank you very much. So thank you very much for the invitation to tell a little bit about what we are doing here at Aarhus University. So Intimate is, of course, focused a lot on age models and how to handle it, how to improve them, and so on. However, age models, we always have problems with age models. That's also part of the marine work, of course, but there is so much happening in these times with better possibilities of dating and so on, that we are really able to step a lot forward in our research. And I would like to take the positive side and not look so much about some issues we might have, but what we can actually get out of it now, because we have so much better age models. So we have been working in northeast Greenland for a while, but the question is, I would like to first address, why are we even sort of going so much focus on the marine? And last time there was talked about ice cores, and there you could see there's a lot of sort of similarities in ice cores, for instance, within Greenland. But if you go into the marine, we really need to have a lot more holes to cover what's going on. And this is just an example that shows the climate record of the last 2,000 years at 3 different spots that are marked on the map to the left. So one, the topmost curve shows the sea surface temperatures based on alkanones north of Iceland. The middle one is the same type of record north of Newfoundland, and the last one is just south of Newfoundland. And you can see none of them look alike. We can explain what's happening here. Some of that is the general cooling trend we've had the last 2,000 years. Some of that is linked to the North Atlantic Oscillation. I'll not go into this detail, but this is just to show why we can't, unfortunately, just rely on one record for one place. It is really complicated. But what do we do? I mean, we can't just go out with a ship, drop down and take a core. We tried to do that before, and it was really hit and miss. So in the process, in order to actually get good results, we try to do acoustics first, sort of sub-bottom profiling, seismics, and so on. And To the left, to the right in the screen, you can see there is a number of different profiles that we use immediately on the ship. We're circling around to trying to find, okay, here there seems to be a sediment package. If you, for instance, look at the middle panel, sort of the B, up in the corner, you can see there are some thin lines and so on. So this is an excellent sediment package. Whoops, let's take a core. Whereas if you go to all the top one under A, that's so much disturbed that is not certainly good for perisonography. That might be good for other things. So that is the first thing we try to do. Then we are also not just happy taking a core at the site. Of course, we need to know what's going on. And here, so we always take a CTD. So a profile that shows temperature, salinity, oxygen, and so on through the water column. That is the next step. And then comes the coring. That's the fun part. So long cores, as you see to the right and in the middle, sort of a gravity cores, piston cores, and it can also be shorter cores where you can have a really good resolution or at the top. But now the work really starts, because when we come home with these cores, cut them open from many different places. These are some of the places where we have cores from. And you can see we are really trying to make holes in the seafloor. Then we start looking at them. Just like in any other kinds of record, there are many different types of proxies that we have to use. None of us can use all of them, but we have a general understanding, and then you are a specialist in a few of them. So they are different micropaleontological records or proxies. There are geochemistry, organic, inorganic geochemistry, sediment types, and of course, most of all in this context, we really need good age models. So when you work in the late Quaternary, it's carbon-14 and sort of lead and cesium and so on that we work with. So this is all something we have been doing on a regular basis. And then we try to put all these information together. So I would like to here show an example of how we've done that from Northeast Greenland. Back in 2017, we had a cruise on this research vessel you see here. It's Dana. It's an old Danish research vessel, and it can tolerate sea ice, but not too much. So there is, when you go there, you also have to find the open water places. So therefore, no straight lines. You just, but to the right, you can see where we managed to take stations with sediment cores. In addition, we have a number of extra CTDs and so on. And then we have seismic or sub-bottom profile lines between all the sites. And I could also mention here that in the colors you can see, I'm not sure if you see my mouse, but up in the top, there are some trenches, or generally going from the ice sheet and out. And it's in the trenches that we have sediments. There's very little sediments in the high areas. So that does give some limits to where we can investigate what's going on. But what we were looking at, we were looking for changes in the retreat or the speed and timing of the retreat of the Northeast Greenland ice sheet after the LGM, and also changes in Holocene and deglaciation, ocean circulation and climate. So I'll take the first part first, so the deglaciation phase. So there has been a lot of discussion on how far did the last glacial maximum ice sheet in fact reach out onto the shelf edge. Some studies indicate with the inner yellow-orange line that it didn't go very far out. Other studies suggest that the ice reached all the way to the Greenland shelf. What we can see based on the little yellow dot seen in the middle of the white square, at that site there, we have a sediment core, and that sediment core is, you see the age model to the right. It's not a oops, that was a bit fast. It's not the most fantastic age model, but you can still see that we have dates going back to 25,000 calibrated years ago, with some reversals, but we basically have the LGM, and we can see that they are continuous marine sediments all the way through. If we go a bit quick, then you can also see that based on the red curve, that we have warm Atlantic water going in all the way during the last glacial maximum. So that means that during the last glacial maximum, at this site, ice did not reach to the shelf edge. So that was just one little spot in the map. But we do also have information here from this trough here, which is called Norske Trough. It's the biggest trough on the Northeast Greenland ice sheet, Northeast Greenland shelf, and where a large part of the ice sheet drained out. The white line shows the sub-bottom profiler sort of data where we have those from, and with dots with white numbers are our sediment cores. Going on, looking first at the sub-bottom profiler data from and comparing that with the core. So the sub-bottom profiler data to the left are just a few examples where the top one, there you can see there are iceberg plow marks. So where there are iceberg plow marks, you do not have an ice sheet. Sediment infill, certainly not a grounded ice. But there are some glacial lineations in the last example. And those bottom topography information we can use to see the extent of the ice. Comparing that with the sediment cores, the sort of columns you see to the right are from 4 different sediment cores, and there you can, or that's where the sediment cores are linked together with the sort of the acoustic data, with the cores marked in this reddish color, and the acoustic data are sort of shown as the black lines. And you can see we have some clear reflectors, so clear changes in sedimentation. We can't see everything what's going on down core because our cores were not long enough. But what we can see is that in at the site closest to the ice, which is the one that's to the left in the picture here, that's very close to the ice sheet. There we have marine conditions all the way to at least 12,500, but likely before 13,000 years ago. And in the one all to the right, that's ST1235G, there we have dates that go back 16,000 years. And we just recently, the PhD student who's working on this, he just found more forams, so we can actually date back in time further. So that indicates that here it was certainly deglaciation at these different levels. When we then put this together, we get sort of like a story. It's not the entire story of what's going on, but we have a good idea how the ice has retreated through the Norske Trough. And so likely the ice did not reach the ice shelf the shelf break, but it had a grounding zone sort of in the mid to outer part of the trough. Then there was sort of like that sort of with the GCW1. Then there was a retreat sort of after the LGM, and it was a bit intermittent. It happened relatively slow and so on. And then first at the sort of after the really end of the LGM and during the deglaciation phase, we had a very rapid ice retreat from this inner grounding zone until basically where further inland than it is today. And how can we say that it was further inland than today? Well, there are some information from cosmogenic isotopes from islands in the area, and we also have information from this inner sediment core that I'll show you in a tiny bit. So this was the first thing. That's how we can use this combination of data to evaluate changes in ice extent and the speed of ice retreat. But then if we then go and say, what happened with the oceanography? Well, here we looked at more of the cores. We are still, this is ongoing work, so we are really not done yet. But if we, generally, you can see that there is today Atlantic water moving up, as you know, with the Gulf Stream up past Svalbard, but a lot of that water turns around and goes southwards again along the margin of the shelf. In the troughs, the Atlantic water also moves towards the ice sheet. Some of this Atlantic water comes directly from Svalbard, marked in red. Other parts marked in purple has just circulated the Arctic Ocean first, but it's still relatively warm Atlantic water. So that means that in the troughs, we have a much warmer conditions than at sort of the shallower areas where we have polar water on top of the Atlantic water. And you can see that here with the red parts showing where you have the Atlantic water in two different transects across the shelf, and the blue and purple are the colder waters. Don't worry that the colors are slightly different. They are from two different papers. So the next step is to look at the sediments. Here we did CT scans. We don't always have that, but then each type of sediment can be characterized to look at what is this, how was the sedimentation type and so on. Then we look at the different parameters, but here what you should look at is to the right, we have the age model. And this is where we can now do a lot more than we could before, because in this part of the world, earlier it was basically impossible to date anything because the samples that you could get for dating were so small, but too small for dating. There are very few foraminifera, but now you can date samples of just 30, 40, 50 foraminifera. And if you have many of them, then it's not so bad if the uncertainty is high. So that has given us a lot of possibilities now. I will just jump over that and look at the assemblages here. So with red is warm water, with blue are cooler, and so on. And you can see we go back before, around 13,000 years ago. Here, close to the close to the ice margin today, or the glacier front, and we had a lot of Atlantic water into the deep troughs until about 8,000 years ago, and then it became reduced. We do have it still today, but not nearly as much. Based on that, we can actually link the connection between Atlantic water and the ice retreat at the site during time. There is not time to go into these details, but I just want to show that this is actually possible, to make these clear links between sea ice contact, glacier front and ocean circulation. We have done the same at other sites. Here is one from Apollonia, which is at the yellow star. And there, the reason I show that is that you might remember that the red species, the warm water species that disappeared at the previous site around 8,000, here they continue. So this is a bit different story again. And if you then look at this part here, this is basically the same data, where you can, to the right, can see sort of an interval where there is an increase in this, if you can see that reddish curve within the box. And that shows that here around 9,000 to 6,000 years ago, there was an increase in Atlantic water again. However, if we then go to yet another site, just to confuse you a bit, then the warmest part, again with red, was from 8,000 to 4,000 years ago. And you might remember at the first site at all, it was really gotten cold because all the warm water species had disappeared. So now we are back at Seidenkrantz. We have a lot of points here, but we actually are still figuring out what is going on. It's not that one record is good, the others are bad. It's simply because water did not penetrate to the ice sheet through the channels at the same time everywhere. And also the uplift after the glaciation and so on would have played a role. So we are right now trying to figure out what happened. We are only 1.5 years into the project. So, and we have 2.5 years more to do it. So I think there's a good chance we will manage to do it, but I can't tell you everything right now. So in conclusion, so we can see the scientific conclusions are that the Northeast Greenland ice sheet did not reach the shelf edge everywhere during the last glacial maximum, but seafloor landforms and acoustic information, as well as sediment cores, can show us a detailed information on sort of ice retreat in different sort of, that it varied a lot over time. Deglaciation started very early, certainly before 16,000 years ago. And the total deglaciation of the shelf was probably finished around 13,000. Second part of the conclusions are that the deglaciation occurred actually at the same time as we had deglaciation. We had immediately influx of Atlantic water, and now we had the chicken and egg problem, right? Did the Atlantic water penetrate in because there was room, because there was no ice, or did the Atlantic water sort of force the ice to retreat? That is something for consideration. But we know that even though we had Atlantic water, we still had extensive sea ice, and that the influx of Atlantic water became reduced about 8,000 years ago, generally, but still some areas we still had the warmest parts later on. However, today we have Atlantic water, but we do not see it nearly as strongly in the assemblages as we did then. So likely the influx of this warm water to the ice sheet during the last during the deglaciation phase, what was much stronger than we have it today. So thank you very much for listening.
And thank you very much, Marit Solveig. That was a very insightful talk, and also showing the complexity of the system, which I find really interesting. Questions. I think we have time for a few questions. So please raise your hand so that we can see if you have a question. If not, I do have questions. I always have questions. I see a question. So please go first.
Hi, hello, good morning. Thank you for your talk, Marit. I have a question regarding like the one comment that you made in one of the first slides regarding the high temperature of the sea surface temperatures during the LGM. How do we explain that? Because that is what my understanding is, because I'm looking to the Iberian Peninsula and we have some SST that are quite warmer and can justify kind of warmer temperatures in this region comparing to the north, but I never saw anyone mention these warm SST in the northern latitudes. How do you explain that?
It's good you asked, because I think this is a misunderstanding. When I show the foramnifera, they are benthic foramnifera in this case here. So it's subsurface waters. And so the sub before the surface is really important here. So we're talking about a water mass that comes in and basically can melt the ice from the bottom, but it's found at a few hundred meters water depth. On top of that, we can still have cold sea ice conditions. So it's not surface waters that was warm during the LGM. That was subsurface waters. Okay. So just a few hundred meters below. And it is sometimes confusing when we are sort of talking fast. So yeah.
Okay, thank you.
Any other question from our audience? I have a little question. You showed this map with the reconstruction of the ice extent during the LGM with these two different, so reaching, one a bit closer to the shelf and one really a bit outward. What is it based on? Is it based on modeling, or is it based on really ice core research?
It's actually based on the one, at least, that suggests that the ice went all the way to the shelf edge is based on bottom topography. So in the moment you see indication of ice topography, there must have been an ice sheet. The issue here is that you do not know when that ice was from. Right. And that's what we are trying to resolve here by looking at the sediment cores. And we really need a much longer course, but this is what we could get at this site here to get down to previous interglacials. But I think you could use this as an example that how important it is that we come in with many different expertise to try to solve a problem, because none of us can do this alone.
Absolutely, yeah. And perhaps another quick question. So you showed that there's a phase with an ice sheet which is a bit outward to the sea, and then a retreat, actually a retreat further than inland than it is today. Just for us, how do you have any idea how fast? Because that's actually I guess for most of us the main question. So when we think about the present day warming, how fast do these events happen?
Well, I'm not 100% sure about from going inland to out again, because we can just see that based on, that's not our work, but that's published work from cosmogenic isotopes, that it there was a time when it was not there, but precisely how long is not sure. However, what we can do is calculate how fast the ice retreated from the inner grounding zone to away. And there it seems we are actually talking a few hundred years. We have not done the final calculations yet. One of our group, Adrien, is working hard on this. I think we're talking about very long distances very quickly.
Right. So that leaves us there. I guess that's a good, probably a good tie point to our next speaker. I don't